All right. Good afternoon, everyone. Thank you again for the introduction. I'm glad to meet you. I've heard your names for a while. My name is T again, and today I'm presenting our work on the MVG mechanism, differential privacy under matrix value query. And this is my collaboration with Alex, Wins, and Pratik, who is also here today. Thank you. We are from Princeton University. A little bit of background. So this session is about differential privacy, and as we all know, so I'm just going to go over this rather quickly. So the main philosophy of differential privacy is such that answering queries should reveal little about any record in the database. Essentially, it means that it ensures the participation of any record should not change the query output too much. And I try to show it in an illustrative way here, where I have two databases which differ by one record, the orange one here. And in differential privacy, we call this neighboring databases. And the plot in the middle shows the distribution of the query output from these two databases, which are the blue line and the orange line. So essentially, differential privacy try to ensure that this distribution don't differ too much for every possible neighboring databases. And this usually is achieved through formal proofs, which is important. Now, differential privacy framework is a nice one because it can be applied to different types of queries, including scalar queries, vector queries, and obviously this work focus will be on matrix query function. And before getting to a matrix one, I want to build up on something more canonical, which is a scalar and vector query functions. An example here I want to show is blood pressure data. If any of us ever go to a hospital, you know that there are two numbers with the blood pressure, one called diastolic, the other one called systolic, the lower and higher number. And the plot on the left here show an example of data where each dot is a data point from a single patient. So here is sort of distribution of the blood pressure from many patients at, let's say, a hospital. And if you look in terms of database, it would look like something at the bottom where you have two columns and a bunch of rows. Each row represent a patient, data of a patient. Now, what if, for example, we want to know average blood pressure? And by average, I mean the average systolic and diastolic, not the average between the two. Now, the query function will become a vector with two elements, one being the average diastolic pressure, the other one will be the average systolic over every patient in the database. And so, for example, here will be something that looks like a 0.55 and 0.56, a vector of two dimensions, and which can be represented as a dot on that plot there. So that is a vector example of vector query function. And now, how do we achieve differential privacy? There are many ways, but a simpler way would be to do noise addition. So here you start from a database, you compute query answer, which I mentioned before. Then you add noise. We are familiar with Laplace, but here I'm gonna use example from the Gaussian mechanism. You'll see the reason why. And you add noise to it, then you get a differentially private answer below here. So rather straightforward. Now, so that's the matrix value query. Obviously, this work is more on the matrix. Sorry, that was a vector query. This work is on a matrix value query. Why matrix? Well, first of all, there are many real-world query functions that are actually nicely represented by matrix value. For example, the kernel matrix in machine learning, the covariance matrix in statistics, or the adjacency matrix in graph theory. And why do we like to represent our function as matrix? Well, there are a few reasons. One of it being the fact that when you represent your function as a matrix, you have information in the structure of the matrix, which can tell you further information. And two, there are also a lot of mathematical tools you can use with matrix. And three, because matrix is quite common, there are a lot of software that can compute matrix operation rather efficiently. So it's a very nice framework to work on. And now I want to give a concrete example of what I mean by a structure of a matrix. So now let's look back at the blood pressure example earlier. Now let's say instead of getting a simple mean, now I want to get a covariance matrix. So from database on the left, the same one. Now on the right, I got a query function, which is now a 2x2 matrix. Covariance is a 2x2 with 4 numbers. So that alone might not look like it tells you much, but knowing the structure of this matrix actually can tell you that the diagonal elements give you the variance of each of the two blood pressure, whereas the off diagonal actually give you the diagonal give you a variance, the off diagonal give you the covariance or correlation between these two blood pressure. So you can see one query of a matrix and actually give you information based on its structure as well. Now the question is, how do we do differential privacy on this type of query function? A simplest way to do it is to add noise that is identically and independently distributed, or i.i.d noise, to each element, which is shown in the figure at the bottom here, where you start with a matrix value query function. Example here shows 2x2, but it applies to any size of the matrix. Then you add the noise that distributed similarly as you show, as you can see from a figure, to each element, and you get the output. So that works. However, it could be very suboptimal because, as you can see, it doesn't really utilize any information about the structure of the query function or the noise. So a better method for this particular case would be to use a noise that is non-i.i.d, which is shown on the figure on the right here. Again, similar to the last figure, except now the noise is not, for each element, is not necessarily distributed similarly. And this can be done in different ways. For example, you can do it by adaptive query, which usually is done by you first query the first element in a differentially private manner, then you look at the result, then you use that information to query the next one, etc. Or you can do from a sampling, using a sampling noise by exponential mechanism, or a multiplicative noise using the JL transform method. However, our approach here that I'll present shortly would like to use something more canonical by using an additive matrix-variate noise. And now I think it's a good time to give a little bit of outline of what I'm going to be talking next. So first, I'm going to present the key tool of our work, which is the Matrix-Variate Gaussian distribution. Then I'll present the main mechanism, which we call the MVG mechanism, stand for Matrix-Variate Gaussian. And finally, I'll conclude with some experiment and discussion. And now let's start with the key idea. So as I mentioned, the key idea of our work on matrix value query and differential privacy is straightforward. We want to use matrix-variate noise, additive matrix-variate noise. And this is shown by a figure at the bottom. Again, you start from query function, which is matrix. I show here as 2x2, but it doesn't have to be symmetric. It doesn't have to be a 2x2. It can be any size. Then what you do is you draw a noise, which is in itself a matrix. Z is a matrix here, and you add to it. So that's the key idea here. Now the question is, what kind of noise do you want to add? Again, there are many ways to do it, but in our work we focus on this matrix distribution called Matrix-Variate Gaussian distribution, or MVG distribution in short. What is MVG? It is essentially a matrix version of the Gaussian distribution. So we all quite familiar with Gaussian. So this is basically take it into a matrix form. And the main difference of this to the normal Gaussian distribution that we are familiar with is the fact that it actually has two covariances. Why? Because one would consider the correlation between the rows, and the other covariance will consider the correlation between the columns, because we are dealing with matrix. Now, what I can do here is I can throw out the PDF, but it would be really hard to absorb here. So what I'm going to do now is I'm going to link the MVG distribution to the distribution of what we kind of know well, which is just i.i.d normal. It turns out we can actually construct the MVG distribution from linear transformation. So I start from the left, number one here, with first, what I'm going to do is I'll draw each element from i.i.d normal and just put them together into a matrix. Here, example to be 3x3. Again, it can be any size. And with this, by construction, we know that every row is i.i.d and every column is also i.i.d. And turns out this is actually an MVG distribution with zero mean and two covariance as identity, straightforward. Then now, what if we want the rows to be non-i.i.d? Well, what you can do is you can do a linear transformation on the left, which I shown as step 2 here. You multiply your random variable with matrix S. You get a new random variable, which is a matrix U. Turns out this U now will have rows that are distributed with covariance sigma, which is a function of your S matrix. And now it can easily be shown that, well, not easily, but it can be shown that this U actually is distributed according to MVG with zero mean and now a covariance sigma on the rows. But the column is still i.i.d, so it still have covariance I for the column. Now the next step is obviously you also want the column to be non-i.i.d. What you do is you do the same thing, but now you do a linear transformation on the right with matrix P. Now your column will become distributed with a covariance psi, which is a function of P, and you get a final random variable Z, which is actually distributed with the MVG distribution of zero mean and the covariance sigma and psi. So that's it. That's a construction of the MVG distribution, rather straightforward and familiar. But again, this is sort of canonical construction. In fact, you can look at it on the left in an analytical form and then get out right away. And with that in place, now we are ready to introduce the MVG mechanism, including its privacy analysis. And so first, the MVG mechanism is fairly straightforward. You first draw matrix random variable Z from the MVG distribution with zero mean and covariance sigma and psi, as I showed earlier. Then you add it to the Curie function. So that's it. However, as you can see here, I actually haven't specified how we choose sigma, the covariance sigma and psi yet. And clearly, this actually should be done in a way that to ensure that the mechanism preserves differential privacy. And I'm going to get to that in a minute. However, due to the complicated nature of the matrix, I would like to give some more intuition into this sigma and psi through something called the singular value decomposition, SVD. And why? Well, first, what it is SVD is a way to decompose a matrix into two components. One is called singular vectors, and another one is called singular values. Here will be the matrix W and lambda. Again, this still doesn't make sense. However, it has a nice geometric interpretation if you consider a Gaussian distribution with this covariance matrix and this decomposition by SVD. Turns out that the singular vectors in this case will actually tell the directions of the noise drawn from this Gaussian distribution, whereas the singular values actually will tell the magnitude of the noise in that direction. So it has really nice interpretation. So example here is shown at the bottom, where let's consider 2 by 2 matrix. You have a sigma covariance, you decompose it with SVD, and I wrote it out explicitly with 2 singular vectors and 2 singular values. And if you look at geometric interpretation in terms of a distribution contour of noise drawn from the Gaussian distribution with this covariance matrix, you see it become an ellipsoid. And the ellipsoid, which is specified by width of which the major and minor axes are specified by the singular values, and the size of each, meaning how distorted the ellipsoid looks, will be depending on the singular values corresponding to that. So that essentially is SVD. And why I'm mentioning it, because it is really important to the proofs of privacy, and this is the main result of our MVG mechanism, which is the privacy analysis. Again, I could throw in a main theorem, but it would be difficult to follow. So I for those interested, I refer to our main paper. So here I would like to give intuition of what it says. So the main theorem says the MVG mechanism preserves epsilon delta differential privacy if the singular values of the 2 covariance matrices that satisfy the privacy condition. And the said privacy condition is sort of in the form here, where it's a function of the 2 singular values, and it is bounded by a constraint. And clearly this constraint is a function of the 2 privacy parameters, and as well as the sensitivity of the Curie function. And to give you more intuition of what this condition means and its implication, I want to show this sort of conceptual plot at the bottom. So this plot is sort of similar to an information geometry plot where you look at the two covariance matrices as the axis. The orange area is a conceptual area that tells you the area where every instance of the MVG mechanism within that area would preserve the same differential privacy. So what this means is it actually gives us a little bit of flexibility. It has a design space for us to do so, and that design space allows us to optimize the utility. And there are many ways to do it. One way to do so is to observe that the privacy condition I mentioned earlier put constraint on the singular values, but not on, the singular value, which is the noise magnitude, but not on the singular vector, which is directions of the noise. So it kind of means what this implies is that we can decide the direction of your noise to maximize utility while preserving the same privacy. And this can be done in many ways. For example, you can do using some domain knowledge, or you can do differentially private SVD, etc. And I'll show an example shortly. So now I'll get to experiment. We did run on a few experiments, but I want to show a sort of a canonical one here, which is simple to follow. So I consider a query function, which is the identity query, just query the database itself. And the dataset is the liver disorder prediction dataset, which has 5 features from blood tests of 248 male individuals. And the task would be to predict the daily average alcohol consumption. So it's a regression task in a sense. And so what we do here is we query the data, train a model on the differentially private data, and then actually try to test it on the real data to see the actual performance. Evaluation metric would be the root mean square error, which is an error matrix. The larger, the worse. The smaller, the better. And again, the query is a matrix of size 6 by 248. And these are some experimental results. Due to the time limit, I won't go through. We have some more comparison in the paper, but I want to just bring out a few ones because of the time. So on the top first row, you can see the performance on the real data, and the second one is give a baseline on random guess. The bottom is the performance from the MVG mechanism using epsilon 1 and delta 1 over the number of samples square. And here, and then we also compare to two methods, which are Gaussian mechanism and the JL transform with the same privacy guarantee. The key note here is the fact that I mentioned earlier how MVG mechanism allows you to utilize some information, some domain knowledge. The result here also use that by looking at some literature that shows that one of the features called ALT is good indicator of this task, and also a knowledge that in regression, the label is important for the success. So these are the two knowledge that we incorporate in the design for the experiment here. And as you can see here, the MVG mechanism performed quite well, and it beats the previous works. Although the performance improvement over GL transform is not significant, but we point out to the runtime comparison that's actually run a lot faster because I think primarily because GL transform involve many modifications of matrices, whereas the MVG is additive, so it's rather straightforward and quick. And now to wrap up, I just want to point out a few points on conclusion. First, our work consider differential privacy under matrix query. And the important takeaway about matrix is the fact that it has structure, which should be exploited in differential privacy. Second, we propose an MVG mechanism, which adds matrix-variate noise, and it has a privacy design space that allows utility to be maximized within that. And finally, I want to conclude with the future works. So at least our vision for this work is that it would be a sort of a framework for a lot of future work to work on differential privacy and matrix query. And one way to do so is we think about optimizing the utility under the privacy design space. So as mentioned, you can do it by looking directions of the noise, etc. And two is, again, the key property about a matrix is the fact that it has structure. So we believe that we can further utilize the structural characteristics of the matrix, both the query and the noise, further to reduce the noise added. And finally, I think it would be interesting to find similar techniques that would provide epsilon differential privacy for matrix value query, possibly a matrix version of Laplace mechanism. And that's it. Thank you very much. Did it do well on time?
Any questions for T? If you have a question, can you please come up from the mic?
As we know, in most of cases, the design of the mechanism to generate the noise just depends on the real application that we would like to apply to. And in your experiment, you referred in the slide 18, you just apply to a very simple function f(x) equals x. Right. So I just wonder whether it is valuable for what kind of scenarios you would like to apply to your mechanism to.
Oh, you mean like in actual other query functions that are metrics?
Yes. As a very example, if we would like to estimate the stress level, we have to use like FFT or something. So it will be complex to generate the noise because the query has been very difficult into frequency domain. So you just apply in a very simple function. So what is the scenario and application?
Well, what you mentioned can work as well because all you need to do is to compute the sensitivity. Yes. So you do a FFT, let's say it's a matrix, yes. And you compute sensitivity, and that's it. You plug it into the mechanism. You just add the noise to it. So it's a output perturbation noise. So it's not like a exponential mechanism where you have to go into the detail. The only thing you need is the sensitivity of your query function.
Actually, I just want to know that, as I know, the frequency transform method just to generate a very small noise and meets the security utility of epsilon. So it was great, I suppose. So what is the obvious advantage of your method comparing to FT method?
Well, like you mentioned, so I'll give an example. For example, if you do metrics like a covariance matrix I showed earlier, that would be a matrix. And as I mentioned, we do have a design space that preserves privacy, and within that you can do optimization, try to optimize the utility, which I believe might cover the other method as well, depending on the privacy guarantee it has.
Okay, thank you.
All right, let's thank Steve once again.